Here are solutions to homework set number 7 for ECE 463-663 Modern Control. This homework set looks at servo compensators. The problem looking at here is try to control a ball in a beam system so that the ball winds up at a given spot in spite of modeling errors. So start out with problem number 1, kind of give an idea what's happening. Here's the linearized dynamics of the system. Same thing we had back from homework set number 4. Let's take a full state feedback control law like we did a little bit earlier. If I want to put the poles, it was like minus 0.8 plus minus j0.8, minus 5, minus 6, I get feedback gains. I can simulate how that works. So here's our nonlinear simulation. I am going to specify the feedback gains. U equals minus kx times x plus kr times r. Here's my states. I'm going to go over and over again, looping. Here's my set point. My control law wants to know the input, find the dynamics. That's the nonlinear dynamics for the ball and beam system. Integrate, display, and here's what she looks like. So run this puppy. There's the ball and beam. I tell it to go to 1. It goes to 1. Tell it to go to minus 1. It goes to minus 1. Okay, not too surprising. Suppose there's a disturbance on the system. And one way to get that is if the mass that I designed for, 2.2, is wrong. Suppose it's actually 2.5 kilograms for the ball. Now when the ball's over here, I have extra torque. The torque is force times distance. That disturbance causes a steady state error. So it no longer tracks. In addition, if I really wanted to, I could say, what happens if I have a sinusoidal set point? So give it a sinusoidal input. It doesn't track a step, and it does a really bad job at tracking a sine wave as well. So that was the solution that we came up with the last 2 weeks, full state feedback. How do I fix that? Well, in the first case, if I want to track a constant set point, you add a servo compensator with a pole at s equals 0. So what that does, this integrates the difference. If r is a constant, at steady state, everybody's a constant. The derivative of constant is 0, so that forces this point to 0. If that's 0, y tracks r at steady state. In addition, if there's a constant disturbance, again this has to go to 0, y still tracks r at steady state. So add a servo compensator and stabilize the system. So here I create the augmented system. Here's the augmented A matrix. And you can see this is A, this is a zeros matrix. Here's your C matrix, and there's your servo compensator, your integrator. The B matrix with respect to U is right here. B matrix with respect to R. C and D. So that's the augmented system, the plant plus the servo compensator. To stabilize it, let's use pole placement. Let's put the poles at minus 4/6 for a settling time of 4 seconds for 2 poles, and the other 3 just out of harm's way. That gives me a set of feedback gains for Kx, Kz, well, 5 gains. The first 4 gains are Kx, the last one's Kz. There's my control law. Now for the linear system, plot the step response. Take the closed loop A matrix, the B matrix with respect to R, C and D, plot the step response, and sure enough, no overshoot. The settling time is roughly 6 seconds-ish, maybe a bit longer. If I take the step response with respect to a disturbance input, then it rejects the constant disturbance. So this control law should do everything. Track a constant set point, reject a constant disturbance. The acid test is try it on the nonlinear model. So in MATLAB, I will go back to a step input, use a different control law. Instead of Kx and Kr, I'll have my feedback gains Kx, Kz. Here's my servo compensator. Your Z dot is 0, pulse at S equals 0. There's the input, something makes it controllable. Down here in the control law, U is now minus kz times z minus kx times x. Integrate x, integrate z, calculate dz, there's my servo. Integrate x, integrate z, and display. So let's go back to the nominal system. If this is 2.2 kilograms, it should work for the nominal system. I tell it to go over to 1. It does. No overshoot. Tell it to go to minus 1. And it does. Okay, that's for the nominal system. Suppose instead the ball was 2.5 kilograms. That means I'll have a constant disturbance and a constant set point. Now tell it to go to 1, and it goes to 1. That's what the integrator does for you. The integrator forces the steady state error for constant input to be 0. It will track as long as you're stable. Okay, so it works pretty well for constant set point. Suppose my set point was a sine wave at 0.6 radians per second. Does it track in this case? And the answer is no, not even close. The servo is designed to track a constant. That's all you get. That's all, the only thing that's guaranteed. Anything other than a constant, it may not track. Well, suppose I did want to track a sine wave. In that case, it's the same solution. Just add a servo compensator. This one has a pole at plus minus j.6. B makes it controllable. So one way to do that is make the servo compensator up. This for the A matrix. Any old 2x2 system with poles at plus minus j.6 works. Pick the B matrix to make it controllable. So here's your augmented system. This right here is your A matrix, zeros matrix, your BZ times C, and your AZ. Here's the B matrix with respect to U, B matrix with respect to R, C and D. Once I form the augmented system, find feedback gains to stabilize it. So here again, I'm going to put the poles at minus 0.5 and somewhere else. Kind of play around with it, try to keep the gain small, but keep the settling time reasonable. That's what I picked. To do that, I get feedback gains. The first 4 gains are kx, the last 2 are kz. Now, if I try it on the linear system, here's the closed loop system. Find the response. I guess I didn't really use that. Using the step 3 command, here's the closed loop A matrix, B matrix with respect to R, C and D. My time points, my initial conditions are 0. My set point is a sine wave. It tracks the sine wave. If I instead make this a B with respect to D, sine wave input, it rejects a disturbance at 0.6 radians per second. The acid test is try it. So programming it, here's the servo compensator's feedback gains, the servo's A matrix, B matrix. Here's my set point. The control law stays about the same. Seeing how that works, we'll run this again. Here's the input for sine wave. It's trying to figure out what the input has to be, the torque, to get it to track the sine wave. So here's locking in on it, and eventually figures out what the sine, cosine terms are, and nails it. That works for sine wave. Let's try it for cosine wave. Again, what the servo is trying to do, it's got 2 states, trying to figure out sine and cosine, what those 2 components are to force it to track. Eventually, when the error goes to 0, you integrate 0, which gives you an integration constant, tells you what the sine and cosine terms are. Thus I can track a sine wave at 0.6 radians per second. Now, kind of one sidelight. This works at 0.6 radians per second. Does it work at DC? So here's a step input. It is doing an absolutely horrible job at DC. And there's one unstable. If I want to track a DC and a sine wave, that's a different design. Another problem with this is if the frequency changes, not part of the homework set, but just for fun. If my set point is actually 0.7 radians per second rather than 0.6, it's dead on at 0.6. At 0.7, it's no longer tracking. If I want to track at 0.7 radians per second, I got to start over, redesign my servo compensator, recalculate my feedback gains, then it works at 0.7. That's kind of a limitation of servo compensators. But if you do know the frequency of the set point, I can track it. And that is with the incorrect mass as well. Homework set number 7 for modern control.